Um, Hi everyone. So this is intended as a supplementary material for chapter 7, since the tutorial haven't got the time to cover this section of the course. This is based on the Frank White fluid mechanics textbook. The video only covers, I think, roughly the first half of chapter 7, but that should get you started on the final assignment. So the chapter is called Flow Past Immersed Body. Immersed, sometimes we kind of think of it or we kind of confuse it with submerge. It doesn't have to be, like say complete submerge in water. Uh, and water, air, they're all fluids. So having a plane or like object in midair traveling, that also counts as a immersed body. So quite often, instead of calling it immersed flow, we call them external flow. Just kind of sounds more intuitive. Basically, what we're looking at today. We're also gonna look at boundary layers, which is pretty important, leading to the meat of the day, drag force. Hopefully, by the end of this video, you'll be able to calculate drag force for simple geometry. So external flow, sometimes also called aerodynamics, there's so many applications. Automotive, cars. So next time you go on the 401 or highway, you can look at those big trucks. The hood is not there to make it look more handsome. It's actually there to improve the performance, the aerodynamic performance of the truck. And something else, there's sometimes a skirt, like a flap, like a skirt there, between the wheels. It's also there to again improve the aerodynamic performance by reducing the drag. Um, Planes, that's a very straightforward classic examples for external flow. Cities. So you can actually run simulations to kind of predict how the flow around a city look like. There's a very active research community on that. You kind of have these quite complicated boundary layer because you have these very three-dimensional objects, and then it interacts with the flow, and then depending on what's in front of that building, also interacts or interferes with it. Honestly, even a basketball or like projectiles, bullets, they all can also count as an external flow application. Now, so there are primarily three main types. They're all technically three-dimensional, but it can be simplified. So our first one is called two-dimensional. The idea is that if you have a technically three-dimensional object, like a cylindrical rod, and then the flow is coming into it like that direction, um, you can actually turn it into two-dimensional problem if the rod is very long. Then you can just take a slice down the middle and say, yeah, I'm only interested in there. I don't really care about what happens at the end. Then that's when we can simplify a three-dimensional problem into a 2D problem. Axisymmetric, another great one. In that case, it's kind of like a bullet-shaped object. That would be your domain. So you have the axes of symmetry. Um, the idea is that when you run simulations, 3D objects are very expensive. And if you can break it down to a simple or more economical two-dimensional domain, this actually reduces the cost quite significantly. Even three-dimensional object can sometimes be kind of broken down a little bit by making it if there's a symmetry plane. So let's say this is the plane. I'm not very good at drawing planes. Kind of came out like a fish. Let's say it's a plane. Now, if the flow is coming straight down, then you can actually just cut a symmetry plane. So rather than simulating the whole thing, we just want the right half, right? the left half, we can just omit it, skip it, and then imagine putting a mirror down the middle. And that actually saves you, again, 50% of the computational cost. Um, might not sound like much, but when your case is, say, 100 core years, saving 54 years is quite significant. Now, quick recap on viscous and inviscous flow. So primarily, this is related to basically the effect of shear or friction. When we're talking about flows in viscous, usually we're looking at area further away from any kind of surface or wake, where the flow is usually more uniform, more streamlined, straight, clean. There's not too much interference or fluctuations. Now, that's usually when we can apply the Bernoulli equation, assuming other conditions are also met. So remember, we cannot apply Bernoulli equation close to the wall because of the effect of friction. And which kind of brings us to viscous flow. So that's usually primarily when you look very close to any kind of wall surface or within the wake of an object, the flow past an object. Uh, when that happens, you can still use, or you have to basically use the energy transport equation, assuming that things like, say, the duct can actually be compensated, or the friction loss can be compensated with, like, say, duct head, pump, etc. Uh, fun fact about the picture on the right or lower right, it's actually taken at the Turbulence Research Lab in the Roseburg building. So this is actually from our lab. We did collaboration. I did collaboration with some of my experimental colleagues, and we presented at a conference back in July. Cool stuff. Now, when you're close to the wall, you get friction. You can kind of think of it similar to how, when you have like an object on a surface, the cracks. There's these, if you zoom in well enough, there's these micro cracks or like uneven texture. They primarily contribute to the friction. And, even with flow, like air or water, it's the same. They're still particle. They're just kind of more rigid rather than having a single solid block. Now, that kind of leads us into our boundary layer. So let's say you have flow coming in, hitting a flat plate, a very skinny flat plate. So if you look into here, if you zoom in, again, you get these like, texture on the surface, just like last slide. And then you have flow coming in, let's say 1 meter per second. Now, there are going to be some air particle here, but you can kind of see they kind of get shielded, right? So they actually have a velocity of 0 meter per second, hypothetically, because, they basically just kind of move around. But if you move further out, far enough, you get 1 meter per second. So, you have 0 and then 1. So the texture, or sorry, the profile is going to be a function. Now, it's probably not going to be linear, at least not for the whole profile. It could be linear, sorry. Yeah, it could be linear and then kind of rounds out towards the end. Or sometimes it might also just be almost parabolic, depending on the application. Eventually, it will reach basically the same velocity at 1 meter per second. Now, this height from 0 to 1 meter per second, that's your delta. That's your basically boundary layer height. Boundary layer BL height. If we're being accurate, technically it's based on the 99% of your free stream velocity. So you count from 0 to 0.99 meter per second in this case. But I think for now, you can just assume that that's the boundary layer height that reaches the free stream velocity. Basically, free stream is basically Earth incoming velocity, or if you move far away, that is becomes the flow becomes inviscid again. Right? If you move far away, inviscid. definitely did not spell it right. And then if you move closer to the wall, viscous. And you can tell it's a function of x, basically how far away you have traveled. Now, Reynolds number. Hopefully, you guys are at least somewhat familiar with this at this point. Um, Rho UL divided by mu. Uh, there are two viscosity. I think mu is the dynamic viscosity. You're also gonna have a kinematic viscosity nu, but we'll talk about that later. So there are primarily two flow regime. That's the third one, but let's focus on laminar flow. So the idea of laminar is everything is quite smooth, it's very organized, very neat, and it's actually reversible. So if you spin it around, you can actually reverse what you've done with the flow, and then it'll end up where you started again. Turbulent, that the flow becomes a lot more chaotic. There's a lot more fluctuations. They can kind of see the streamlines kind of all broken up, etc. Um, yeah, it can almost kind of connect it with stuff like chaos theory. Fun fact, when my supervisor started his PhD, he studies turbulence experimentally. He had a colleague, a fellow PhD student that was doing numerical work into turbulence, and that was back in the 80s when computers first started. Uh, his colleague dropped out and quit the PhD program to go work as what we would probably call quantitative finance nowadays in Switzerland. Um, yeah, I think the colleague probably retired before my supervisor even got his tenure. Anyway, so now some of you might have recognized that the Reynolds number to switch over to turbulence doesn't match what we have from chapter 6. Right? In chapter 6, the Reynolds number switch over a lot sooner. That's because if you look at the Reynolds number from a Moody chart, so that's a rho VD. D, that's the diameter of the duct. So when you look at different geometry, different flow, you use different Reynolds number. And subsequently, quite often, the Reynolds number to transition are also different. Now, another thing with the Moody chart, so you have your laminar here, and then these are basically all your turbulent, this whole segment on the right. There's a little pocket called a transitional range. Now, the transitional range isn't laminar, and it's definitely not turbulent either. It's somewhere in between, and you can probably kind of say, oh yeah, it just kind of, suddenly shot up. Um, so transitional flow is quite complicated. Um, and real flow, it's not a light switch. We don't go from laminar to turbulent just because you exceeded the Reynolds number by 0.01. There's a somewhat gradual transition. Uh, Sometimes well, technically it is a third flow regime, but transitional flow is so complicated that quite often we tend to avoid it, or we try to minimize it. Say, because sometimes we can't avoid it. The flow over an object is going to transition to turbulent, but in that case, we want to promote the transition as soon as possible. The main reason is that we know limited when it comes to turbulence, and in a grand scheme of things, I think we know almost next to nothing about transitional flow in a grand scheme of things. Sometimes we have a critical transition, kind of like a pseudo light switch. Are you quit? It depends on that. That will give us different formula to calculate drag coefficient and things like that for flow over a plate. Okay, the meat of today, drag force, FD. Not that kind of drag, aerodynamic drag. So you have the flow coming in, that's your V. If we're being accurate, we use something called the free stream velocity. They say the velocity before it hits an object, because imagine if you look at here, the velocity close to the wall is basically zero, like the boundary layer. And then if you use that and plug it into your drag force equation, you're like, yeah, there's no drag force. Not true. So that's why we want to usually take the velocity further away. And we call that free stream. Now, so FD equals half CD rho V squared. CD drag coefficient is dimensionless. You either find that in a chart or you calculate it or you look it up on a table or it might be given as the part of the problem. Fun fact, so this is actually based on chapter 5. Pi 1 is your drag coefficient, CD. It represents, it's basically a function of your Reynolds number. So we basically kind of rearranged it to come back to a form that gives us a drag force rather than the drag coefficient. Now, the right-hand side, your Reynolds number is a function of Reynolds number, which is why that also kind of contributes to it. When your Reynolds number increases and changes the flow regime, your drag coefficient quite often also changes. The area. Now, we're working with quite often three-dimensional objects, right? What area do we pick? And that's a great question, and it's a whole can of worm as well. However, there are primarily three types. This basically depends on the geometry and also how the flow hits your object. So first one, for stuff like, say, sphere, a very long rectangular block, or like a cylinder, we call those bluff bodies, then we use the frontal area. So let's say this is where the velocity come in, and then imagine your eye is here, and then you look into that. So that area becomes just a rectangle because you're looking in from the front. Sometimes it's also called the projected view. I think one of the final, I think a year or 2 years ago, they used a Christmas tree. A Christmas tree shape is kind of like that. In that case, the projection area just turns into a triangle, right? Nothing too fancy. Now, second, platform, or quite often these imply stuff like plates or airfoils. So with plates, the idea is that you assume the thickness of the plate is so thin that it doesn't contribute much to the drag, and primarily the surface area is what contributes to it. In this case, you have flow over a plate, top-down view, just your plate area. Now, there is a bit of a trap when it comes to calculating drag force for a plate. If you have flow, if the plate is in the middle, as this is your velocity, placed in the middle, you have to multiply the drag force afterwards because you're gonna have flow on both sides. And quite often, even when I was doing some practice a couple of days ago, I forgot to multiply it for one of the questions I was practicing on. Now, finally, for marine applications, boats. Some of you might remember this. So J plus R equals T. Jack plus Rose equals Titanic. So with boats, now we're actually focusing on their submerged area, surface area. It's called weathered area. We have a jargon. The idea is that you want to basically look at the surface area of the object below the water line. These are quite hard to calculate for real geometry like boats, etc., and barges. So this will usually be given to you as a problem at this scope. Unless you're just tracking an oil drum that's being towed along, then in that case, you can calculate the surface area of the submerged section. Now, there's a four-step guides to basically solving drag problems, 4 or 4.5. So first of all, Reynolds number, because again, our drag coefficient is a function of Reynolds number. So you're gonna need your Reynolds number to actually find the drag coefficient quite often. Now, so step two, these are primarily for plates. The step two overall doesn't change if you are working with other geometry, but these additional info only applies for plates. So depending on your Reynolds number, which is why you have to calculate it to start with, you're gonna have a drag coefficient. You can see this is a function of the Reynolds number. And also your delta. Remember, this is the boundary layer height going from 0 to 1. That's your delta. Oops. And x basically the length. So you actually have to put down where you're trying to find the boundary layer height delta. So put it in right there. So that depends on how far it is from the start of the object. Uh, Now transitional. This is where the RU transitional, or I think yeah, a couple of slides ago I called it RU crit. So the idea of flat plate, depending on your RU crit or RU transitional, you're gonna have one or the other drag coefficient calculation formula. These are based on the turbulent one, but then some modification to account for the transitional flow. So again, basically depending on what you get, if you get like, if they told you that the RU transition is 5 times 10 to the 5, then you use the first equation. They tell you it's a second one, then you use the second equation. Now third, that's you're finding your area type. Primarily, it's either going to be frontal or top down. Top down for plate, frontal for other geometry, like a cylinder, Christmas tree, etc. Could also be wetted area, but in that case, it would normally be provided. Finally, you assemble your drag equation. FD is equal to half CD rho V squared A. And don't forget this. You might have to double it afterwards. Kind of leads us into our first problem. And I recommend having this box on your crib sheet. Obviously, you're still going to need other equations, but stuff like the drag coefficient for turbulent or laminar plate will be provided in the official A sheet. Remember, times 2, maybe. It doesn't always times 2. But for flat plates, if they're asking for the drag overall, multiply it by 2 after you found the force. If they only want that one side, they will very explicitly state the drag for one side only.